Welcome back. In today's video, we are going to be moving on to the next big step in our problem-solving toolkit. We're going to be looking at the ability to search in problems where there is time. So up until now, if you haven't really thought about it too strongly, right, we've been working in these standard examples where obstacles are static. They are walls, they are blocked. It is a binary operation. They're either blocked or they're free. They do not move, they do not change. Of course, they could not move because there was not yet time. Now, of course, we all know as humans, right, that real problems very often have time involved as we move towards, these more complicated versions of the problems we're trying to solve. Well, yeah, often there are moving obstacles, there are dynamic obstacles. The amount of time it takes you to drive to work will absolutely depend on the time of day that you're driving, right? So the costs of our edges and actions can also vary with time. And in general, yeah, real life, of course, has time. These type of problems, as we're going to see, are unfortunately substantially harder for us to tackle. And so we have to come up with really clever ways of handling this effectively. So the first thing, I'm going to walk through a really fun example over here to kind of get used to how we're going to search with time. I'm also going to introduce the time expanded A star, so TXA star algorithm, which is going to be our next step where we slightly modify A star to be able to again solve the new version of the problem we're trying to solve. In the meantime, the first thing I want to talk about though is this idea of, okay, so what makes this problem actually specifically so much harder? Let's comment on those characteristics. So the very first one here is that really the actual search space is just going to explode even further. So the search space grows rapidly. Yeah, so these problems are extremely hard because time adds so much extra. It's an entire new dimension for us. At every possible location, you need to consider every possible time step that it was reachable, that it was feasibly found during search. We'll see that the search trees then are going to be massive creatures, of course, and this is where so much of the complexity comes in. Next, one of the main issues is, well, already in standard grid map and other pathfinding examples, well, there are all these different issues of symmetric versions of the same path that's actually really bogging down our search. Well, this problem grows substantially worse in time because now we start to see all these symmetric equivalent version of paths where we arrive at a location at a specific time. Before we get into the actual example here, we're just saying that we have some player, we have Mario, and we have essentially a door. So this location at D is blocked. We can't reach it. Well, if you start looking and thinking about the ways that we can arrive at C, I'm going to write these over time, right? So as time progresses, well, I could move to B here, and then move to C, and then wait, because D is blocked, right? We can't go yet until afterwards. So we see this equivalent move. Well, the same path, what happens if we wait one time step at A instead? Okay, well then you see this, but what happens if we wait at one time step at B first? Then we see this, and you start to see that there is this massive issue of symmetry versions of the same path where you are waiting at different locations, but they all correspond to you doing essentially the same thing. You're in the same solution set. So waiting creates many equivalent paths. That's going to be an issue. It's again increasing the difficulty of actually searching and reaching things appropriately. Now, the final version of this is just that, in addition, time actually makes termination very, very tricky, very challenging to deal with and to recognize. Time, unlike being able to explore, right, it's usually easy in a standard grid map to say, hey, we've explored all of the nodes. Okay, great, I couldn't find a path. Evidently, it must not be, there must not be a solution available. Well, in time it's a bit confusing because the algorithm is uninformed about whether waiting will reach a new outcome yet, right? You don't know if this door will open in the future if you're just doing some naive reasoning. And so because of that, essentially, right, we have that the arrow of time, it's infinite. We don't know how long this could go. How long do we set our time horizon? How long do we continue searching? How do we set reasonable bounds on our time? So all of this comes together to just say that the idea of knowing when to terminate, so termination with time is tricky. This is a harder problem as well. Okay, so then the next thing I want to talk about here is how we're going to choose heuristics in a time-dependent world. So the heuristics we've been looking at, of course, are not related to time. So we can come up with time-based heuristics. What's important there is that these are actually usually vary, again, just because of the nature of how much more difficult the problem is. Time-based heuristics are actually very expensive. So I won't go into some of those in this video, but what we often do instead then, right, like we have this idea that searching with time is really expensive. Well, what ends up happening then and what proves really useful in real problems is actually just to have really fundamental understanding of the real grid distances in your actual problem, right? The real non-time related distances. Obviously these can increase and change based on the real problem, but these form a good basis. Now, we don't often choose to use things like the Manhattan distance anymore because it is not going to be accurate enough. It can be really, really misled. So we're trying to strike this middle ground. What ends up being performative in practice is to still use heuristics that don't have time built in, but we want them to be the really strong versions of the estimates. So what that means is we often use strong 2D heuristics. So these are things like our CPDs and differential heuristics that we've just looked at in the previous videos. So yeah, these are much stronger, more oracle-based heuristics, right? They give us much better estimates of the actual distance, which means that they're letting search hopefully progress a lot better. Now, the issue with these, right, is you have these massive precomputation. You can do that, right? But like, obviously there's this massive trade-off where you do still have to have the time to do this, particularly for CPDs, right? Like when we're working with time, we're still trying to usually solve this in real time. A lot of problems still demand you don't have a perfect working model of the world. You're dropped into a problem, you have to solve it as fast as you can, you need to start moving. In the case that you don't have the time or the resources for CPDs, well, differential heuristics definitely help, but they also still have their own components. You have to pre-compute you need to already have pre-computed the pivots and have that stored. So what's kind of interesting in these domains as well then is that we actually often just run essentially the 2D heuristics, but in an online setting. It's still worthwhile because the speed of the regular search with time can be extremely slow, especially with time expanded A-star. We will, in future videos, show you that there are actually going to be substantially better ways we can easily improve upon the A-star algorithm in the context of time. Well, regardless, it's often useful to compute these online. So the pros of this is, right, we're getting very strong estimates of the actual distance because we're using the good heuristics, but we're actually spending the time to reason in an online setting. Hey, I'm doing this computation, I'm choosing my pivots, I'm calculating, I'm running the UCS, I'm running a Dijkstra's backwards. But I'm doing this, the reason we're doing this online is because now I don't have to run this, right, and store it for every target. I know my exact target. I have some start location, I know my target. So I will just run a single Dijkstra's and then store the results that way. Right, that's kind of like this online setting. We're computing the table and caching the table online. Now this is really also useful if your start positions change a lot more than your target. But yeah, there's obviously cons associated with all of this where You still have to run a UCS online before the actual TXA star search. And of course, still caching all of the tables is still prohibitive, especially if the target changes and you have to keep adding more or caching more tables or continuing to do the work. So all of this is hopefully just to convince you that problems with time are substantially harder, and we are going to have to work with different ways to try to get about this and to tackle these problems. I'm going to walk through a simple example over here. I'll erase this quickly and then we'll get started. Okay, so let's have a look then at how this little example would work for TXA star. I'm starting to look at TXA star. But this isn't explicitly just TXA star, this is just new versions of nodes. So unlike before, where our nodes, right, would correspond to a state, and the state is just the XY location, well, so our state now, instead of course just the XY, it's going to need to be XY, T. We need the additional information. These are the worst curly brackets the world's ever seen. Okay, so let's walk through a simple example. We are a Mario player. Congratulations, here we are as Mario. We're starting at location A. I want to make it over to here. This is the goal. However, there is a rock in the way. However, there is a thwomp in the way. Did not have to look that up, I swear. So essentially what's happening is you can treat this in any way, right? We now have this idea of dynamic obstacles. Things are blocked at specific points in time, but they're not always blocked. So here we have essentially an obstacle that is blocking the location D up until time step 5. At that point it will raise, right? And we have a small window that the player will have to run underneath to continue on its way. Okay, so let's start having a look at how the search tree progresses from here. The first thing I'm going to do is to also rewrite the node. We of course didn't need just A, we need now A at time step 0. Okay, so our nodes look a little bit different. We still have the same idea though. Now, at the location A, the very first thing we see, we can of course move to B at time step 1. Great, so we're assuming that every action here is just a single time step. That's usually how these problems work. You absolutely can do it where maybe you take 2 time steps to make a traversal, but then things become really complicated in terms of your collision checking, which we will talk about very soon. Nonetheless, it's usually just a one-to-one relationship. Okay, so now not only can I move to B, here is where the element of time comes in as well. I absolutely have the ability to simply stay at my current location A, and I will now be there at time step 1. Okay, so now I will continue the trend, and let's keep going. So we could continue to move to C at time step 2. That's looking great. Well, we can obviously absolutely go to B as well at time step 2. Right, so we essentially stay at location B. Now, there is another third option. We can move back to A, okay? So, unlike in a regular grid map, it's usually easy to just say, never generate your parent again, right? Like you say, okay, there's no need ever going back from the path I just took. That makes a lot of sense in a standard 2D static situation. Problems with time make this different. We have to now start generating these as potential options. In problems with time, we do have to consider these as valid options. Why is that? Well, let's try to have a look. So imagine there was another obstacle, another thwomp at C as well. So sometimes the only valid solution is the sequence of actions where we're at C and we're about to get squished. So we need to move to D. It's only available for 1 time step, so we need to get out of the way of D, and we are allowed to move back. Say E is in the lava or something right now, and we move back to C, right? So there are these sequence of events where because of the moving obstacles, well, this is a different node. A at time step 2 is absolutely not the same as A at time step 0. Obstacles move, threats move. This is a different problem. We really need to return to the idea of generating a parent. Of course, we'd never generate the parent at time step 0, but that's also not how time works. The arrow of time continues in one direction. Okay, so we also have the idea of that from location A, we still have the same two options. So we can move to B at time step 2, which we now start to see that this becomes interesting, right? How are we going to deal with, we're identifying our first duplicate, okay? Then as well, we can continue staying at A at time step 2. There's another duplicate, but it's also, you're reaching it via different routes. But this is starting to look really dumb, right? This is the idea I drew before, right, where you have all these different equivalent paths when you're waiting. Waiting really complicates the search tree. Look how massive this is for simply moving 2 locations in a straight line. In a straight line towards the target as well. From C, here's where it gets interesting, right? Because we cannot continue to D because it's not yet time step 5. We have all of these waiting actions remaining. So you would have to wait at time step 3, ... right? There's a lot of ... here going on. And then you also have the option to move back B at time step 3 as well. Well, from B, you can move to C at 3, but also to B at 3. And then you could also move back to A at 3. And so forth. There is a nightmare of symmetries and repetitions and different versions of the same path that all are the same cost, and we're spending all this time waiting. Searching with time is difficult. Now, there are a few ways to deal with this. Time expanded A star, to get this out of the way simply, what I was drawing here is just a regular search node tree. Time expanded A star is exactly the same as A star. Literally the only difference is that the states are x, y, t, right? We're still using some form of heuristic function. You could define that in terms of time. We're probably just using one of grid distance, right? These 2D heuristics. But time expanded A star is tracking, essentially it's just adding time to your states to the recognition of duplicate nodes, things like this. Now, there is the idea that when we achieve the same node, we can do the same thing as regular A star, where we have the closed list, right? So we can essentially throw out information based on choosing the one version of the path. So that's kind of fun, but we still generate this and then have to check the closed list, have to find the duplicate, and then either update the information or discard it. So it's still clogging up all of our time and work. We're seeing a lot of issues with this. I want to introduce something called what is the no passing property. Okay, this is an assumption we often make in problems with time that greatly simplifies our overall search tree and our reasoning. So we essentially the no passing principle, the no passing property, this is just stating that I can never achieve a shortcut. I can never get to my goal sooner by waiting now instead of moving first, okay? So what we're saying is when we see these equivalent versions of the path, well, the no passing property would say, well, there's no reason me waiting at A, right? I can already move to B. I will move to B first. This is the version of the path that has me moving and changing location in the environment. Simply by waiting at A, I'm never going to get a benefit, right? We know that at some point we're just going to get to C, and we will have to wait at C. And so through this reasoning of the no passing property, well, we can greatly reduce the size of the search tree. This will be mostly applicable when we look at next week's video on safe interval path planning, SIP, which is a much improved version of search with time. And in that video, we're really kind of, the algorithm has implicitly built in this no passing property to really also make the problem substantially more easy to tackle. I just want to note that the no passing property is extremely useful, just as a very simple rule of thumb, but note that this is actually not technically always true in the real world, which is easy to forget. I think the perfect example, I often try to query students and can they come up with real examples. sometimes you can. I think people go into these like, oh, you get like games of chicken on the road, things like this, maybe in a tunnel, things like that. So you can come up with all these examples. I think the really easy one is just trains, right? Depending on where you live in Melbourne, right, we have express trains. There are some trains that go expressly faster to a location you're trying to reach, and it skips a bunch of stations along the way, right? It's an express train. It'll skip these 5 and then get to the location faster. So there are 2 versions of the train on different tracks. Well, you could take the train right now that is going to stop at 20 different stations along the way, or I take this express train straight to Geelong, and I'm able to actually, by waiting 5 minutes to get the later train, well, I can arrive sooner than I otherwise would. So there's in the real world, the no passing property isn't always true, but nonetheless, it proves a pretty useful tool just for starting to tackle these problems. Okay, so the last thing I just want to have a look at, I just want to essentially prompt you on this. I will do a separate video on this because I think how you store the data is interesting and will make this video a bit longer than it should be. But essentially, right, like we now have this idea of moving obstacles, okay? So what that means is we need a way of actually like tracking this information, storing this information. Is that in frame? Yeah, nice. So this is the worst looking cube the world's ever seen, but this is a cube. Obstacles move at some point in time in order to verify that a state is correct, right? In order to actually verify that when we looked to move to D at 4, right, that is not valid because the door is closed or the obstacle is there. Well, we need this database, what we're going to be calling a reservation table, right, to check, is there an obstacle here at this location at this current time step? So this is essentially what we're calling a reservation table, right? Obstacles move in the world and they reserve their location at specific points in time. So this guy here, this thwomp, well, if I were to draw this, maybe I'll just draw this as an abstract sense. Well, we have some other obstacle similarly, right? We're going to have a train. We're going to have a pink train. It occupies, let's say it's location 1, 2, 3, 1, 2, 3. So what we're looking at here is X location, Y location, and time. So the time axis is this vertical, this 3D component now. When an object reserves, so we're reserving the location 3, 1 at time step 0, right? So time step 0, 1, 2, 3. Well, this location is this cube, this voxel here in this grid. Then we're saying that the obstacle stays at the same location for the next time step, right? So it's reserving 3, 1, 1. Then the obstacle is going to move. So it's going to move from 3, 1 to 3, 2 at, well, we'll say it's at time step 1 as well. That's kind of confusing, right? So it's moving to 3, 2. That's over here in the same time step. So this would be an obstacle that maybe is longer, right? A train might have a carriage. So it is moving through time. In the beginning, it was occupying this one cell. As it goes across, right, it's currently occupying 2 cells at the same location. And then as we continue, right, we can do 3, 2, 2, and we would also reserve that location. So essentially, if I keep this simple, you will have this version of the path, however it looks, that obstacles are reserving their locations in the reservation table. Now the reservation table tracks all moving obstacles, right? So there will be multiple obstacles in here that you can see. Obviously they can never reserve the same location at the same time. Some objects, right, will have this diagonal version because they can't occupy 2 cells at the same time step. Really depends on the kind of problem you're solving, but you are going to need some way of storing this information. We call this a reservation table, and in another video we'll have a quick look at, well, how can we actually make decisions on how to implement this, because it needs to be efficient, right? We need to be efficiently able to query this table and to retrieve the collisions as fast as possible. All of this is really to do with the additional idea of collision avoidance. So on top of everything else, right, we now have two types of collisions. Because objects are moving for the first time, right, now that there's time, obstacles can move. Well, you have versions of collisions. Two agents are moving into the same cell at the same time. They want to occupy the same vertex, the same node, the same location in your graph. This is our standard version of collision. Up until now, we haven't really given this a name, but in the context of graphs, right, this is a vertex collision. Same location at the same time. Right, so you cannot be at the same location at the same time. Of course, you're hitting each other. The other version of this that's new now, though, is the idea that there is also edge collisions. So if I have two moving obstacles, one is at location A and one is at location B, well, they're going to cross. I would say, okay, well, neither of them are reserving the same location, right? So realistically, in terms of your nodes, it seems fine. Hey, it was A at 0 and B at 0, and now it's A at 1 and B at 1. Ta-da, right? That seemed happy. Now we have to do this additional reasoning every time we try to look for a valid node, for a valid move. So when we expand a node, when we're generating its children, well, we need to make sure that there was not a crossing, an illegal crossing of agents in situations where there are those kind of collisions. But most problems do, right? Like if you have a series of trains, they hit each other, of course. They can't go along the same track in opposite directions. These are edge collisions, right? It's your actions along the edges of your graph. Edge collision. And this is where essentially you have two agents crossing an edge at the same time, as opposed to two agents, 1 and 2, occupying the same vertex at the same time. Okay, this I think is a good intro into the idea of searching with time. We're going to explore this a lot more, particularly in the next video where we look at safe interval path planning, which really is a much more performative version of TXA star. So please join me there and as we continue with our pathfinding journey. So thanks for watching, cheers.